We now present the performance analysis of this random coding scheme. We will show that the probability of the error event, that is w hat is not equal to w, can be made arbitrarily small by a suitable choice of parameters. Consider the probability of the error event, which can be written as summation from w equals 1 up to m, the probability of the error event conditioning on w equals small w, times the probability of w equals small w. Now the probability of the error event, given w equals small w, is simply equal to the probability of the error event, given w is equal to 1. This is so by the symmetry of the construction of the random coding scheme, specifically because all the code words are generated randomly in exactly the same fashion. Because the probability of the error event, given w is equal to 1, does not depend on w, it can be taken outside the summation. Now summing the probability that w is equal to small w for small w from 1 up to m is simply equal to 1. And therefore, we have shown that the probability of the error event is equal to the probability of the error event given that w is equal to 1. So, without loss of generality, we assume that the message 1 is chosen. This is illustrated in the figure, in which the first code word, x to the 1, is sent through the channel to obtain the received sequence y. Now for w from 1 up to m, define the event EW equals the event that x to the w and y are jointly delta typical. That is, the code word for message w and the received sequence y are jointly delta typical. Now observe that if E1 occurs, but EW does not occur for all w from 2 up to m, then no decoding error would occur, because according to our decoding rule, the received sequence y would be decoded to message 1. Therefore, the probability of E1 intersect E2 complement, intersect E3 complement, intersect all the way to EM complement, given that w is equal to 1, is upper bounded by the probability that the error event does not occur, given that w is equal to 1. Now consider the probability of the error event, given that w is equal to 1. This is equal to 1 minus the probability that the error event does not occur, given that w is equal to 1. Using the above inequality, we obtain the upper bound 1 minus the probability of E1 intersect E2 complement, intersect E3 complement, intersect all the way to EM complement, given that w is equal to 1. This is simply equal to the probability of the complement of E1 intersect E2 complement, intersect E3 complement, intersect all the way to EM complement, given that w is equal to 1. Now, by means of De Morgan's law, we can write this event as E1 complement union E2 union E3 union all the way to EM. Then, by the union bound, the probability of the error event, given that w is equal to 1, is upper bounded by the probability of E1 complements, given w equals 1, plus summation w equals 2 up to m, the probability of EW, given w is equal to 1. By the strong joint AEP, the probability of E1 complement, given w is equal to 1, that is, the probability that x tilde 1, the first code word, and the received sequence y are not jointly delta typical, given that w is equal to 1, is less than some small quantity nu that goes to 0 as delta goes to 0. This is illustrated in the figure. Now conditioning on w equals 1, that is, the first coword has been sent, for w equals 2 up to m, x tilde w and the received sequence y are NIID copies of the pair of generic random variables x prime y prime, where x prime has the same distribution as x and y prime has the same distribution as y. It is because all the cowords are generated in exactly the same way, and so they have the same distribution, namely px to the power n. Since the DMC is memoryless, x prime and y prime are independent. The idea here is that the coword x tilde 1 is independent of all the cowords x tilde 2 up to x tilde m. Because the received sequence y is obtained through the transmission of the coword x tilde 1, intuitively x tilde 2 up to x tilde m are independent of y. Now for w equals 2 up to m, the probability of EW given w equals 1 is equal to the probability that the coword x tilde w and the received sequence y are jointly delta-typical, given that w is equal to 1. By lemma 7.17, this is upper bounded by 2 to the power minus n times the mutual information between x and y minus tau, where tau goes to 0 as delta goes to 0. Note that our choice of m satisfies 1 over n times log m is less than the mutual information between x and y minus epsilon over 4. And this implies that m, the total number of messages, is less than 2 to the power n times ixy minus epsilon over 4. Therefore, the probability of the error event, which is equal to the probability of the error events given that w is equal to 1, is upper bounded by the probability of E1 complements given w equals 1, which is less than nu, plus summation w equals 2 up to m, the probability of EW given that w is equal to 1, which is less than or equal to 2 to the power minus n times ixy minus tau. Now in this summation, the number of terms is upper bounded by 2 to the power n times ixy minus epsilon over 4. Now this ixy and this ixy cancel with each other, and so we have nu plus 2 to the power minus n times epsilon over 4 minus tau. Now let us take a closer look at this term, 2 to the power minus n times epsilon over 4 minus tau. Recall that epsilon is fixed. Since tau tends to 0 as delta tends to 0, we can choose delta to be sufficiently small so that epsilon over 4 minus tau is greater than 0. If so, 2 to the power minus n times epsilon over 4 minus tau would tends to 0 as n tends to infinity. Now let nu be less than epsilon over 3, which is so for a sufficiently small delta, and let n be sufficiently large so that 2 to the power minus n times epsilon over 4 minus tau is less than epsilon over 6. Then we obtain the probability of the error event less than epsilon over 3 plus epsilon over 6, which is equal to epsilon over 2. Thus, we have shown that with a suitable choice of parameters, for the random coding scheme, the probability of the error event is less than epsilon over 2 for any arbitrarily small epsilon, when n is sufficiently large. The idea of the analysis is the following. First of all, let the block length n be large. Then by the joint AEP, the probability that x to the 1, that is the code word being sent, is jointly typical with the received sequence y would tend to 1. At the same time, the probability that any other code word is jointly typical with the received sequence y is approximately equal to 2 to the power minus n times the mutual information between x and y. If the size of the codebook, that is m, grows at a rate strictly less than the mutual information between x and y, then the probability that the code word x to the w, jointly typical with the sequence y, for some w not equal to 1, can be made arbitrarily small. Then the probability of the error event, that is w hat not equal to w, can be made arbitrarily small. We have already shown that for the random coding scheme, the probability of the error event can be made arbitrarily small. We now show the existence of a deterministic coding scheme that can do the same. According to the random coding scheme, the probability of the error event can be written as the summation over all codebook C, the probability of the codebook C being chosen, times the probability of the error event for that codebook C. In other words, the probability of the error event is a weighted average of the probability of the error event over all the codebooks. Then there exists at least one codebook C star such that the probability of error, PE, is less than or equal to the probability of error weighted over all the possible codebooks, which we have shown is less than epsilon over 2. And by construction, this codebook has rate 1 over n times log m greater than IXY minus epsilon over 2. By letting Px be the input distribution that achieves the channel capacity, the rate of this code can be arbitrarily close to the channel capacity. To complete the proof of the achievability of the channel coding theorem, we are now going to show that from this deterministic code with PE, the average probability of error, less than epsilon over 2, we can construct another deterministic code whose maximal conditional probability of error, lambda max, is less than epsilon. Without loss of generality, assume that the conditional probability of errors are in ascending order. That is, lambda 1 less than or equal to lambda 2 less than or equal to all the way to lambda m. From PE less than epsilon over 2, we have 1 over m times summation w equals 1 up to m lambda w less than epsilon over 2. This implies that the summation of all the lambda w's is less than m over 2 times epsilon. Since m is even, m over 2 is an integer. Then the second half of the summation, namely summation w equals m over 2 plus 1 to m lambda w, which is upper bounded by the summation w equals 1 up to m lambda w, is less than m over 2 times epsilon. Thus we have shown that the second half of the summation is less than m over 2 times epsilon. From this, we have 1 over m over 2 times the second half of the summation is less than epsilon. As there are exactly m over 2 terms in the second half of the summation, this means that the average of all the lambda w's for w from m over 2 plus 1 to m is less than epsilon. Since we assume that lambda w are in ascending order, the smallest value in the second half of the summation, namely lambda m over 2 plus 1, is less than epsilon. And this implies that lambda m over 2, which is less than or equal to lambda m over 2 plus 1, is also less than epsilon. The conclusion is that if the average probability of error, PE, is less than epsilon over 2, then lambda 1, lambda 2 up to lambda m over 2 are all less than epsilon. Thus, by discarding the worst half of the cowords in the code book C star, namely those cowords that correspond to lambda m over 2 plus 1 up to lambda m, we obtain a new code book with lambda max less than epsilon. After discarding the worst half of C star, the rate of the code becomes 1 over n times log m over 2, because the size of the message set, instead of m, is now equal to m over 2. Now this is equal to 1 over n times log m minus 1 over n, where 1 over n times log m is greater than ixy minus epsilon over 2. By letting n be sufficiently large so that 1 over n is less than epsilon over 2, this is greater than ixy minus epsilon. Here, we assume that the decoding function is unchanged, so that the deletion of the worst half of the cowords does not affect the conditional probabilities of error of the remaining cowords. This completes the proof of the achievability of the channel coding theorem.